So a circle inscribes an isosceles triangle of side 3, 3, 4 units. A rhombus ABCD with side 13 in turn inscribes the circle. Uh, okay, find AC into BD. Again, we start whenever we see like something that at least sounds sort of complex in terms of diagram, we start with like every piece of it and then we sort of make a diagram out of this. So inscribed onto this triangle of sides 3, 3, 4. So there is a circle first of all, and it inscribes the isosceles of sides 3, 3, 4. In 3, 3, and 4. And a rhombus ABCD with side 13 in turn inscribes this circle. So like there is a rhombus here which inscribes this circle. Ignore this part, please. So it is ABCD, and we have to find AC into BD. First things first, like we obviously like we know the side of the rhombus, so and a rhombus if each side is equal, so all sides will be 13. So we know this, and we know the side of the triangle, right? Now, obviously, like for finding the like what do we know about the rhombus, right? Like what relation do we know that can help us to find the diagonals? First, we know that in a rhombus the diagonals are perpendicular. Like I'm just trying to list down the relations that we know for a rhombus that involve diagonals because that is what the question asks. The diagonals are perpendicular, but here again the figure itself has no diagonal side. Like there's no, and we already know the side, so there's no like sort of use of applying Pythagoras etc. even if we know that the diagonals are at 90 degrees. The second thing we know about the diagonals is that the area of a rhombus is basically half into d1 into d2. In general, and this is again a concept related to this, in general area of any quadrilateral on this planet will always be half into product of diagonals into sine theta. This is true for all quadrilaterals in the world every time, right? So this sine theta is the intersection angle between the diagonals. So if the diagonals intersect at let's say 30 degrees, so it will be sine 30. For rhombus, the diagonals are perpendicular, so it will be it turns into sine 90, and we get this formula for a rhombus, half d1 into d2. Now it starts to sort of make a bit of sense, right? Because we know the area of a rhombus has this formula, and we know that the rhombus has a circle inside it, right? So there should, like, if we know the area and there's a circle inside of it, it should immediately strike me that this should have something to do with the in radius. And as we discussed yesterday, right, the r is equal to a upon s is valid for all figures, not only for triangles. We discussed this yesterday. So this is a universal relation. So now I know that, okay, S I can get because all sides are given. A has those diagonals here. So if somehow I can get R, I can find out the diagonal product. Because this and this I would have gotten in that case. So basically this question is basically around finding this R. So basically finding the radius of this circle. Of this inscribed circle, right? Now the radius of this circle I can readily find out. I know the sides of this triangle. Isosceles triangle is 3, 3, 4. I know that the circumradius, this radius would be the circumradius, is basically ABC upon 4 into area. Area of an isosceles triangle you can find by Heron's, which will give the correct answer, but a shorter formula for isosceles is b by 4 root 4a square minus b square. B is the different side. So this will be 4 upon 4, which is 1. 4a square is 4 into 3 square, which is 9, so 36, minus b square is 16. So this is root 20 or 2 root 5. So this is the area of this triangle. So the circumradius would be 3 into 3 into 4, which is 36 upon 2 root 5, which is 18 upon root 5. This is the circumradius of this, which will be the in radius of the rhombus, because this is a circle outside of this and this is a circle inside of the rhombus. So this will be equal to the in radius for the rhombus. So in this formula, if we just put 18 over root 5 is basically a upon s, which is a is like to be found half into d1 into d2. S is basically 26 here. So you can find out a from this equation and compare that to half into d1 into d2. You multiply 2 and you will get the d1 into d2, which is what is asked in the question, right? So basically again the question then boils down to basically finding this out. Once we found this out, then getting the area when all the other things are known, and then comparing area to half d1 into d2. d1 into d2 is what the question asks, and that's it. But the major, so again the solution itself is not difficult. striking the fact that, okay, how can I link diagonals to, what is being asked in the question? That is the only part of the puzzle actually. So once we realize that, okay, diagonals feature in the area formula and the area can be linked because there is a circle, so there should be something to do with the end radius, and we can easily figure that out from this triangle. So if, let me just draw you a diagram for this thing. So if this is a triangle and this is a circle, so this circle touches like all the vertices, so this will be the circle of this triangle. If I draw another rhombus outside of this circle, such that the circle is inside within this, so this same circle will be the in circle of the rhombus. So this same circle is the circumcircle of the triangle and the in circle of the rhombus. So which is why the radius will be the same, right? The circle is the same. So the circumradius of this triangle will be the end radius of the rhombus. Right. And the only other principle here that was involved is remembering that R is equal to A by S is always applicable. So yeah. Other than that, it just uses the usual formulas of circumradius and etc. This is CAT 2018 possibly, so or 19 probably. But let ABC be a right angle isosceles triangle with hypotenuse BC. BQC be a semicircle away from A. This is important, away from A. So BQC be a semicircle with diameter BC. So with diameter BC, you can draw a semicircle on this side or on this side. But since it says away from A, it will be away from A. So it will be this side. So let's say this is a semicircle, right? This is point B just for us. And this is the diameter. This is important. And let BPC be an arc of the circle centered at A and lying between BC and BQC. So BPC be an arc of a circle centered at A. So this is the center of that arc and lying between BC and BQC. This was BQC. So between these two, there has to be an arc which is centered at A. So basically, this will be a part of a bigger circle which is centered at A. Just complete the circle. This is the one. So this is the center, and you have the circle wherein the arc is what is given as this thing. So this is called BPC. If AB equal to 6, find the area enclosed by BPC and BQC. So this area. Right. And you may have seen variations of like such questions, right, wherein there's a sum figure and you have to calculate the area enclosed between two of its segments or whatever. Right. And in all these questions, the concept is the same, that you have to sort of break the figure into the figures that you know, like triangles, rectangles, squares, or semicircle, etc., wherein you can figure out the area like into standard figures, right? And sort of have like you have to make this portion in sort of a combination of those standard figures so that the area can be calculated, right? So here also we'll do the similar thing. Okay, so again, how to, and in this will work in every question involving like areas enclosed and everything, right? Just break the figures into figures that you know. So here in this case, if I call this this is an arc, so basically this is a triangle. If we call this area as X, this area as Y. So essentially this area is nothing but area of the semicircle. This is the entire semicircle minus Y, right? Minus Y. Okay. And Y itself is basically this quadrant area. How do I know that it's a quadrant? They only said it's an arc, but since it's a right angle triangle, so a quadrant with a central angle of an arc with a central angle of 90 degrees is a quadrant. So this is a quadrant. So Y itself is difference between quadrant and triangle. Right. Now these areas are readily known. For example, this is a right angle isosceles, so this would be 6 and this would be 6. So triangle area I readily know as half into 6 into 6, which is 18. Quadrant area is the radius is 6 of this quadrant. Quadrant is 1/4 of a circle, so it will be pi r square by 4. So which is 6 square by 4, which is 9. So 9 pi. So basically this Y is nothing but 9 pi minus 18. Area of the semicircle, so this has to be subtracted from this entire semicircle. The semicircle was on a diameter BC, so we know that this hypotenuse will be 6 root 2, direct Pythagoras, like 6 6 and 6 root 2. So the radius of this semicircle would be 3 root 2. Area of semicircle would be pi r square by 2, so pi into 3 root 2 square by 2. 3 root 2 square is 18, so 18 by 2 is 9, so 9 pi. So this is the area of semicircle. Again, we took the radius and pi r square by 2, that's it. So this is 9 pi. So basically the required area is this. So which is 9 pi minus 9 pi minus 18, which is 18. That's it. So nothing too fancy, just a direct. Basically this question, the only catch is to draw the diagram from a written problem. In a triangle PQR, the in circle touches the sides QR, RP, PQ at TUS respectively. The radius of circle is 4. The lengths of QT, RU and PS are consecutive integers. Find the area of the triangle PQR. So here again, the diagram shouldn't be a problem. The diagram is pretty direct. Triangle PQR, the in circle touches the circle QR, RP and PQ. QR is T, RP touches at U and PQ touches at S. If the radius of the circle is 4, so basically the in radius say is 4, and the lengths of QT, RU, PS are consecutive integers. So basically this and PS are consecutive integers, right? So again, consecutive integers they have written, so we can take something like x plus 1, x plus 2, x plus 3, but in any, like whenever you're given a case across any topic, not only for geometry, if you have to take consecutive integers, right, always take numbers such that the calculation becomes easier. So instead of taking x plus 1, x plus 2, x plus 3, we can just take QT, yeah. So x minus 1, x and x plus 1. Just to sort of make the calculations a bit easier, we can take, and this like funda works across this thing. Even in questions like, let's say if you have questions on AP and GP, right? When you said that, okay, like there are like 3 numbers in arithmetic progressions and you have to choose like 3 numbers in arithmetic progression. So instead of taking A plus D, A plus 2D, it's always better to take A minus D, A and A plus D, so that the calculation gets a bit easier. The same thing here, basically, right? So let me just. So again, wherever like I'm feeling that the concepts are such that they can be applied across different topics, I'm just mentioning them there as well, right? So x minus 1, x and x plus 1, all this is given data, nothing from our side. The only thing we that know is now the in radius is equal to 4, which is given. What do we need now? We'll get to the solution, but let's like try to figure out the thought process behind this. Area of the triangle we need to know, right? Area of the triangle needs to be found out, and the radius of the circle is given. Basically, the in radius is given. So all I really need is the semi-perimeter. This is one way to find out. The other way to find out could be if we have a different mechanism to calculate the area, then we can compare the two areas and get it. Like here, the semi-perimeter, basically we don't know the sides, right? We only know the in radius, and we know that, okay, not sides, like segments of these sides are consecutive, like, and these are 3 like random sides when they are consecutive, right? But we don't know the entire sides. Is there a way to figure out the entire sides? That should be my first question here. Like that should be a question which should strike you right on, like when you read this question for the first time, right? Is there a way to figure out the sides? Because if there is a way I can figure out S, R I already know, I can get the area. So if this is x minus 1, we know that in a circle, if the tangents are drawn from the same point, the tangents are equal. So this will be x minus 1, so this will be x minus 1. QS, that is. Similarly, this is x plus 1, this is x plus 1. Similarly, this is x, so this is x. Tangents from same external point are equal. Okay. So now I sort of have the sides as if just to write down the sides. So PQ is basically x minus 1 plus x plus 1, which is 2x. QR is basically 2x minus 1, and PR is basically 2x plus 1. So now I know the 3 sides, right? I can figure out the semi-perimeter, even though it's in terms of x, but I can figure out the semi-perimeter, right? So it is basically 2x, 2x minus 1, 2x plus 1, the sum would be 6x. So the semi-perimeter is 3x, correct? Okay. Now the in radius is 4, the semi-perimeter is 3x. So technically the area should be 12x, but we don't know x. This should be the area, we don't know x. So what we need to find out here is that, can I figure out an area by some other method also, such that then we can equate this area to that area and figure out x? Is there a way to do it? So yes, there is a way to do it. And how do I figure that out? Basically, now I have the size in terms of x, so I can use our favorite Heron's formula as well, right? So 12x is the area here. Okay, not a favorite, it's basically cumbersome, but yeah, like it's a popular formula. So Heron's is basically 2x and 2x minus 1 and 2x plus 1. And why am I doing this once again? Because I have an area by one formula, but I don't know x. To figure out this x, I need to have another area so I can equate those two areas and figure out x. So Heron's will be s is 3x, and you just have to take the gap of this. So basically, a is equal to 3x minus 2x plus 1 will be x plus 1, and this will be x minus 1. Okay, so this will be again combining x plus 1, x minus 1, and this is so basically 3x square into x square minus 1. And again, this is the area, and this is should be equal to 12x, right? So basically, if I just sort of, uh, you know, bring the x square outside of it, right? Or basically, you can just square at this point as well, right? 144x square is equal to 3x4 minus 3x square. If you cancel out x square, so this will be x square, this will be nothing, right? So 3x square will be equal to 150, x square will be equal to, no, 3x square will be equal to 147, so x square will be equal to 49. If 3 comes here, x will be equal to 7. So the area would be 12 into x, which is 84 square units. That is the answer. So good question, combining multiple concepts of equal tangents, and then basically 12x and the Heron's formula we just equated to sort of get the value of x, and x was equal to 7, and the 12x gave us the area directly as 84 square units. Okay, a paper of length 24 centimeter and breadth 18 centimeters folded such that the opposite vertices of the diagonals coincide. Find the length of the crease form. This problem actually you will find in any standard book, because this is sort of an independent variety of a problem. If you haven't seen this, it's difficult to visualize. But basically, if this is a piece of rectangular piece of paper, right, and if you fold it such that basically this end, opposite vertices of the diagonals coincide, if that this end comes here, there'll be a crease formed, right? And you can take any two diagonals. You can like start folding from here and reach this. You can start folding from here and reach this, or like whatever, basically, right? And in each case, there'll be a crease formed, basically, right? And this question is probably on every group in some form or the other. And there is a crease formed which was something like when you fold the paper, like when you if you fold it from top down, there'll be a crease formed. Like let's say you're folding it from here, you start folding it from here, there'll be a crease formed here. And this is what the length that you have to find out is. So length is 24 and breadth is 18. And the crease will always be a slant line. It obviously you can visualize, right? If you fold a real paper, and then you can visualize, right? It will be here, and this is the length that we have to find out. And again, important detail is that it's a rectangle. Now, the reason why this question is sort of important is because one thing is obviously like it's sort of a different figure than the other diagrams, but also the concept here is that whenever you have a paper folding scenario, right, the crease will always be a perpendicular bisector to the diagonal. We'll just repeat that. The crease will always be a perpendicular bisector to this diagonal, or to any, like you can draw any diagonal, but basically, yeah. So this part will be equal to this part, or the diagonal will be a perpendicular bisector to the crease actually. So this part will be equal to this part. Why is this? Because you're folding across the diagonal itself, right? You're basically coinciding. If I were to just name this, right, and pardon the like this thing in the diagram, but yeah. So if you fold from D to B, right, keeping like across the diagonal, then the diagonal will be a perpendicular bisector. The diagonal will sort of divide this tree symmetrically, always. So this is 90, this is 90, and this is like 2 halves. So like maybe would be easier if you had like a real piece of paper, right? So you can just visualize it better. So basically, in all such questions, right, they'll always say that opposite vertices of the diagonals coincide. To say that, okay, if you start folding from point D and you sort of go on folding it till the point D coincide with point B, right? You fold it in a way that the D becomes the point B basically. Then when you open the paper back, there'll be a line, there'll be a crease formed. And since you folded it across a diagonal, that diagonal will divide the crease symmetrically. So that diagonal becomes sort of the axis of your fold in a way. So that divides the crease equally, always. And equally, and that's a perpendicular bisector too. Like your crease will be formed perpendicularly to the diagonal. If you can visualize it with like a real paper, if you have one nearby, then yeah, you can even visualize this. But yeah, so this is the concept that is getting involved in this question. That this would be a perpendicular bisector to the crease. Now, once we know this, right? So basically, this is 90, and these two are equal. So if let's say labeling the crease as MN and P. So if I find, like, the question is basically around the length of MN. If I find Pn, let's say, I can just double that to get the length of Mn. So if I find Pn, that should be good enough. Okay, so now think about this, right? Let's say, what do I need to do to get this length of Pn? Whenever the sides are unknown, right, and there is no like clear mechanism of, let's say, something as direct as Pythagoras getting applied or something, some.
Sure.
Yeah.
Just one question that is it I would say mandatory that the uh, diagonals will divide that
Yes.
crease in equal halves
Yes. Always.
always?
Always. 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 The diagonal will always be a perpendicular bisector to the crease. Because
Okay.
think about it, like, don't mug it up. Just think about it that if you're folding something about an axis, right, then the result of that fold will be symmetric across that axis, right? Like think about it in a, like, in the reverse way. Like, why should one length be more than the other if you're folding across a diagonal?
No, it's a law of symmetry, no?
Yeah, like there's no law as such, but yeah, in general, like if you have to see, basically, if this figure was an irregular, like if this figure was some weird quadrilateral, let's say like this or something like this, right? Like this is a triangle, but yeah, some weird quadrilateral was there, then yeah, then it won't be symmetric. But if it's a rectangle, right, so then it would still be a, in fact, even in this case, it would be a perpendicular bisector, but there in that case, we won't have like direct lengths and all to figure out. But here, in the rectangle, the diagonal will always and always, to your question, be a perpendicular bisector of the crease.
So the area will be half.
No, the area would not be half. So if you're asking that whether the area of this part will be the same as this part, in a rectangle, yes, but in the other quadrilaterals, no.
No, I'm talking about this rectangle.
Yeah, in the rectangle, yes. In a rectangle, yes, it would be equal. Because again, if you're folding it across a certain axis, right, so then around that axis, the areas will be equal. So this area will be equal to this area. And whenever you see a question on paper folding or length of the crease, or if it was the other way around, that they would have given the length of the crease and asked you to find the ratio of the length or breadth or whatever, always remember this, that the diagonal will be a perpendicular bisector to the crease. Why? Again, because the folding takes place across that diagonal, so it will be the geometry of it will be symmetric across that diagonal. Now I have Pn is a part of, so again, there is no direct way to sort of find the length of this, because there is no like Pythagoras or something like Apollonius or whatever getting applied here, right? We don't know those many
Sure.
dimensions here. Yeah. Actually, so no, the idea is good. The only problem with that is, first of all, it won't be a rhombus as such. The rhombus means all sides equal. If you would have said
Oh,
parallelogram, yes,
sorry.
parallelogram can
Parallel.
be found, yeah. So that's correct, like that's a good point. But it won't be a rhombus, because for that, dm would need to be equal to dn, which we don't know. And even if we like construct this parallelogram, right, to basically get this, and parallelogram, in a parallelogram, diagonals bisect each other, which is also working out here. So it's fine. But the thing is that to get this, we need to then get the length of this diagonal, because then only we can do the by 2 of, or like basically if we get the length of this diagonal, then we are done for the question. But there is no direct length of this node. We don't know how long is BN, how long is DM to figure that out.
So in this case, the length DB is perpendicular bisector or just a bisector of MN?
It's perpendicular bisector.
Okay.
It's perpendicular bisector, yeah. Because again, this again goes from the fact that it will be symmetric across this diagonal. So when symmetric means like everything in like these two basically components will be equal. So like it will divide into two equal halves in terms of side and in terms of angle. So both will be 90-90. So there's a perpendicular and bisector. So yeah.
So this can be approached via area method. I can think in that direction. We can
Again,
get
a good lead, yeah. But how would you find the sides here? The main challenge is finding out side
no,
because
no,
we know
no.
the length is the breadth. Yeah.
We can get the diagonal DB as
Okay. Root over 18 square plus
root
24.
over here, correct?
Yeah.
And then area of a parallelogram is equals to half d1 d2 into sine theta.
But
Okay.
do we know one of the diagonals? Like, do we like, so like there has to be two sides to an equation, right? Let's just write what you're suggesting. It's a good chain of thought. So just let's just discuss that. So you're saying that area of a parallelogram would be half d1 into d2. Okay. D1 we can figure out that is root over 18 square plus 24 square. That is correct what you said. So this number we know basically. This number we don't know. And this is actually what we have to figure out in the question. So it's again one equation and two variables. Area also we don't know, right? So that is why like in this equation there will be, we don't know the area and we don't know the diagonal. So that will be a problem. So which is why basically, so and if you like the area of a parallelogram, the standard formula for area of a parallelogram is base into height, right? So if like the height is 18, okay, rectangle like sides are parallel, so the height will be 18. Height we know. But the base for this parallelogram is BN, we don't know the length. If we would have known the length, then yes, we could have found out the area, and from this equation we would have found out the D2. But yeah, we don't know the area because we don't know this length BN. Again, let me just repeat. If we had known BN, we could have found out the area by BN into 18 and equated it to this to get the D2. So essentially, like no direct way to find out the sides by concepts that we like readily know, like Pythagoras or Apollonius or whichever like formulas give us the sides, uh, length, etc. So usually, like in these cases where something is not like readily available, the first,
I got it.
yeah, please go ahead.
Through similar triangles, triangle DAB and take one triangle MPB. Okay. Uh, so for DAB, we have all three sides, and for MPB, we have a diagonal PB, a half of diagonal PB.
Yeah,
So we have two, so we can use that and find MP.
fantastic. Yeah, that's the absolutely the correct approach, and so pretty well done. So basically, like the first suspect when I'm not getting lens readily, like here there's no concept that can be immediately applied. So the first thing that you need to look at is similarity. And after similarity, can we prove some triangles are similar? Now we know that this angle is 90, right? We just discussed. And this is 90 because it's a rectangle. So if I see triangle PNB, here this is 90. And if I take this triangle ABD, uh, like ABD here, even in this, the big triangle, this will be 90. And in both these triangles, there is a common angle B. So I can write these two triangles as similar because two of the angles are same, right? So P and B, again, to yesterday's point, once again, the naming of the triangles is of critical importance here, right? So the B is common between both, so B will come in place of B. P is 90-degree here, so the 90-degree from here should come A, which is A here, and then the remaining, which is D, should come here. So P and B similar to triangle A, D, B. So well done there. That's the similarity was the correct here. So now if we just like we have just proved this triangle similar by AA. So if we just write the ratios, right? So PN by AD, again the first two here, is equal to NB by DB equal to PB by AB. So PN by AD AD is what? 18. NB, etc. Like NB is this, we don't know, so we don't need to use this part of it. We can just directly compare the first and the third. PB, we can know because it is the diagonal upon half. So PB is basically root over 18 square plus 24 square by 2. Now, what is a quick way to figure out a diagonal of 18 and 24? Like, you can obviously calculate it, but what is a quick way? If you see that this is in the ratio of 3:4, so this would be 5 from Pythagoras triplet. So this is 18, 24, this would be 30. So half of this would be 15. So PB would be 15 by AB, 24. So PN is 15 into 18 by 24. So again, like a specific variety of a question where if you've seen this, you'll be able to do it immediately. Cool. So, and once you strike that, then the rest of it is just similarity equations, right? So this, and again, the quicker way to do it would have been 1824, the hypotenuse is 30 because the 3, 4, 5 triplet works. Some triplets are like useful to just remember because their proportions, like here there was a proportion of 3, 4, 5, 6, 8, 10 is also a proportion of 3, 4, 5. Then there is like 9, 20, 21 is also a triplet. There is also one with 8, 15, 17. Right. Some of these are the only initial ones, at least are just good to sort of know. So, and of course there's 5, 12, 13 here.